reverse convolution for image restoration. What if I told you that one of the most fundamental operations in deep learning, transposed convolution, isn't actually doing what its name suggests? Today, we're diving into groundbreaking research from Nanjing University that introduces the first true reverse convolution operator for neural networks. This is Converse 2D, and it's changing how we think about image restoration tasks like denoising, super-resolution, and deblurring. Let's start with the problem. Standard convolution is everywhere in neural networks. It extracts features and reduces spatial dimensions. When we need to go the other direction, to upsample images, we typically use transposed convolution. But here's the catch. Transposed convolution isn't a true inverse operation. It works by inserting zeros between input elements and then applying a regular convolution. Mathematically, it doesn't actually reverse what convolution does. Previous approaches have significant limitations. Classical deconvolution methods require iterative optimization and are specialized for specific tasks like deblurring. Invertible convolutions impose strict constraints, such as requiring identical input-output shapes, which limits their use in deep networks. We needed something better, something that could serve as a true mathematical inverse while being flexible enough for modern neural architectures. So, how did the researchers solve this? They formulated reverse convolution as a regularized least squares optimization problem. Given an output y from a convolution operation, they want to reconstruct the original input x. The beauty of their approach is that it has a closed-form analytical solution using fast Fourier transforms. This means no iterative optimization. It computes the reverse in a single step, making it efficient enough for deep learning. Let me explain the key innovation here. The optimization problem includes two terms. The first term ensures that when you convolve and downsample the estimated input, you get back the observed output. The second term is a regularization that keeps the solution stable and close to an initial estimate. By solving this mathematically, they derived a closed-form solution that can be implemented efficiently using FFT operations. They built this operator into what they call a converse block, inspired by transformer architecture. The converse 2D operator handles spatial dependencies, while one-by-one convolutions enable channel mixing. Add layer normalization and GELU activation, and you have a powerful, flexible building block. The implementation includes learnable parameters. The convolution kernel K can be learned end-to-end during training, and the regularization parameter lambda is learned per channel, allowing the network to adapt to different feature characteristics. Now let's talk about the applications and results. The team built 3 networks to demonstrate the effectiveness of their operator. Converse DN-CNN for denoising, Converse SRRsNet for super-resolution, and Converse USRNet for deblurring. Each network replaces conventional convolution and transposed convolution layers with their proposed converse 2D operator and blocks. For Gaussian denoising with noise level 25, Converse DN-CNN achieves 30.7 decibels PSNR on the SET12 dataset, outperforming both standard convolution and transposed convolution variants. The visual results show that Converse DN-CNN produces cleaner results without the border artifacts that plague traditional deconvolution methods. This is particularly important because one of the historical challenges with deconvolution has been handling image boundaries effectively. In super-resolution experiments with 4 times upscaling, Converse SRRsNet achieves competitive performance across multiple benchmark datasets including SET5, SET14, BSD100, and Urban 100. The results demonstrate that Converse 2D can effectively replace conventional upsampling modules without sacrificing reconstruction quality. Perhaps most impressively, in the deblurring task, Converse USRNet achieves 38.4 decibels PSNR on motion blur, significantly outperforming the baseline. What makes this particularly interesting is that the operator can directly condition on blur kernels at the feature level, giving it an advantage over methods that operate only on RGB images. The network works in a 64-dimensional feature space, allowing for much richer representations than traditional 3-channel image domain approaches. So what makes this work so important? For the first time, we have a principled, mathematically rigorous reverse convolution operator that can be seamlessly integrated into any neural network architecture. The contributions are threefold. First, a novel operator with a closed-form solution derived from first principles. Second, a flexible building block inspired by transformers that separate spatial and channel processing. And third, strong empirical results across multiple image restoration tasks. This research opens new directions for designing learnable inverse operators in deep learning. The code is available on GitHub, and the paper was presented at ICCV 2025 in Honolulu, Hawaii. As neural networks continue to evolve, having mathematically principled operations like Converse 2D will be crucial for building more interpretable and effective models. Remember, sometimes the most impactful innovations come from questioning the fundamentals we take for granted. By asking whether transposed convolution truly reverses convolution, these researchers have given us a new tool that's both theoretically sound and practically effective. Thank you for watching.